So now to export it from Cloud Compare and into QGIS, we're going to first export it as an ASCII file. So for that, what we need to do is go to the tools, go to projection, rasterize and contour plot. We can keep the step size as 1 and the active layer is the cell height values. The direction is Z, cell height is minimum, and the empty cells can be filled in with the Kriging interpolation. Let's update grid, and this basically will give you a preview here. As you can see, this looks a little bit weird. We can't get too much of detail at this point, but what we're going to do is click on cloud, and this is going to export it as a cloud into the layer panel. So I'm just going to click OK here, and we get this sort of a meshed out layer, which is using just the ground points. See, based off of the ground points, it is just filled up the gaps in between to get an average of the area pretty much. And it's not an exact average, it is using an algorithm called Kriging, and it has interpolated or filled in those gap values. Once we've got the ground points raster, we can just quickly check how the off-ground points look. The off-ground being the trees, mainly the canopy. We can just see it and move it around and just make sure that it looks all right. Let's see this part here. Is that good? Yeah, seems all right to me. And the idea is to play around with it, look at it from different angles and see if it makes sense. And then to save the layer, we're going to make sure that this is the selected active layer. Go to and then click on save. Now here we're going to save it in the inputs folder of the QGIS project. So if this is the QGIS project in inputs, and I already saved it here, let's just go ahead and save it again as the same CC ground points, and let's just call it 2 because I already have a file here. The file type is ASCII cloud, and I'm just going to click on save. Let's leave all of these as default values, hit OK. And then we're going to see if we can directly drop it into QGIS. When we're working with Cloud Compare, let's make sure to keep saving it after each stage just so that we don't lose any information. And for that, you're just going to go to File, click on Save Project, make sure it's the same project name as we'd used before, and it's going to be a .bin file. Click Save, and it should overwrite the save file. Okay, so now over in QGIS, we're going to attempt to drag and drop this ASCII point cloud. And so what I'm going to do is click on this, and this is about a 15.3 MB file. Just drag it and drop it into QGIS. Now it has imported. The funny thing is, in Cloud Compare and QGIS, both being open source, it does have some glitches. So this step of importing the ASCII DTM raster, which is an output of Cloud Compare, it doesn't always import properly back into QGIS. In this case it has, and this question mark arises because the CRS has not been set, which is the coordinate reference system. That is an easy enough fix, but the last time I tried it, it did not import. And that is because the output from Cloud Compare was not optimal. Somehow after it restarted, it worked again. But these are things you just need to understand about open source tooling and sort of work around it. For example, let me just show you. This time it imported, but the previous ASCII file I generated, which was this, if I attempt to drag it and drop it, you're going to get an invalid data source error. But the workaround is that we're going to use a Python script, a tooling which I have made in this case, to directly polish out the DTM before we import it back. And we're going to go ahead and do that now. Okay, so this is the tooling I have, and what it does is it's a pretty basic interface. You first select the directory, and as you can see, I already have some previous directories set, one of them being the current project we're working on, or we can just start a new directory here. And once the directory is added, you can see all of the ASCII files in the dropdown. As seen here, there are 2 ASCII files which we've created just now, which has the suffix 2. I'm just going to select that. And of course, this step is just translating the .asc file to a GeoTIFF file with some smoothing and other functionality in between. We can leave all of the default settings pretty much, but this is how we're going to do it. We're going to load the point cloud. We can leave the voxel size the same. There's a small tooltip which tells you what each of these options does. The generation of the 2.5D mesh, we're going to leave it all the same, all of these different algorithms, the different iteration values, and the correct CRS. In my case, I'm using EPSG 32643, which is an output from WebODM. All of the DTMs and the orthos follow this coordinate reference system, given the input of mapping within India, in my case, from a drone. So after all of these settings are set, and as I mentioned, the default values here, I'm just going to click on run all steps, and it should run. We can see a log describing what is happening, and the pipeline is complete. It is exported to this location, which is the same input directory which we were working with. And so now if we head back to the directory, we can see that the TIFF file has been generated. Now before we import it back into QGIS, we're just going to clip it to the boundary so that we can compare it apples to apples with the DTM which we initially had, which was a direct output of the web ODM or photogrammetry process. So for clipping the DTM or the TIFF file into the boundary of the area of interest we're working with, I've made another tool just to make things a little easier. This is a survey toolkit. I'm going to click on the raster clipper, and again it's a similar kind of workflow where we select the project directory, and because everything is structured in this standardized way, the drop downs will populate based on what exists in the particular folder. For example, here I'm going to select the boundary file which we need, and of course the project directory is set to the project we're working on, and I'm going to select the TIFF, which was an output of the ASCII to TIFF conversion in the point cloud tool. So as we can see here, this is CC cloud compare ground points 2, which was the one we were working with, and we have these suffixes of the actual values which were used to export the TIFF file. So I'm just going to go ahead and select that and hit run clipping. Now once it's clipped, the tool knows where to drop the file, and that's going to be in the boundary clip DTMs folder. And so now when I head back into QGIS, I'm going to go back from inputs into sessions, boundary clipped DTMs, and just select the most recent one, which will be our TIFF file which we've generated, and then I'm just going to go ahead and drag it and drop it in here. So now we have a clean DTM from the cloud compare process. After that little bit of a cleanup, we didn't do the manual cleanup here because it wasn't necessary. The cloud simulation filter seemed to do a good job with the default values, but now we have this, and of course we can't really compare it appropriately with the previous DTM, which is nicely color shaded through the colored hillshade script. So we're going to apply the colored hillshade script on this as well. And for that, as mentioned, there is a script we have. And what we're going to do is now go to the Python console button here. Let's select the show editor, and it's already on the script here, the generate hillshade script. We have a detail about how to use the script. There's a how to use body of text in the script, but we don't really need to look too much into it. I'm just going to go ahead with using it. But mainly I need to select a layer with DTM as a suffix, and there has to be only one layer which is selected which has DTM in the suffix. So I'm going to use the most recent file which we've added in, that's the DTM, and I'm just going to hit run. After it runs, we can see that the hillshade has been generated, and now this should be comparable with the previous hillshade. Let me just go ahead and select the previous hillshade, and then I'm going to come back here with the new hillshade, and there we have it. We have the difference in the two hillshades. We can see that this is more smoothed out. It seems a bit blurry, but you notice that here we don't have that blob anymore. So that in fact was erroneous in the initial digital terrain model, which didn't have the algorithms of choice and which didn't use cloud compare for cleanups and more specific cloud processing algorithms. And you can see the difference here. The valley seems to be okay. It seems to have done a decent job at the valley in the previous step itself. But here with our processing pipeline of first using cloud compare, exporting the ASCII, and then using the point cloud tool to convert the ASCII into TIFF with some more smoothing parameters, we have a DTM which we can work with, and this DTM is more accurate. We'll be going with this. As you can see, the hill is much more like the actual hill which we saw in the 3D model when we were playing around with it, much more representative of the actual surface of the land. Before we move forward, there is one thing I want to change. If you notice, this part of the DTM seems to have lost some information. In the previous default DTM, this is filled up, but here in our cleaned up DTM, we've lost some information here, that chunk. And so what I've done is I've run the CSF, the cloth simulation filter again, with a value of 1.8. And 1.8 means that the cloth grid is going to be tighter which means it is going to allow less trees or less projections to be classified as non-ground, meaning you're going to get more points for the ground. And you can see how this fills up here in this part especially. So let's go with 1.8 instead of the default value of 2, and let's convert it to the DTM imported back to see if we've gathered that lost information. Okay, so I have actually gone ahead and made a couple of tweaks to the Cloud Compare ground point classification. The first one was I set the CSF to be 1.8 instead of the default 2.0 for the cloth resolution in the CSF algorithm. And for the interpolation, instead of the Kriging algorithm, which does the plates stacked in that certain way, I've selected it to be empty. So that looks something like this. This was the Kriging for 1.8, and then this is how it looks when it's empty. So meaning it's not really filled it up with an algorithm in here. However, in the point cloud classification tooling which I've made, it does interpolate it with its own algorithms, and that turns out to be much smoother. So this is how this looks. This is the default WebODM hill shade. Then we did the Kriging. As you can see, there are plates stacked. And then finally, we have the, in the Kriging, there's the hill. In the Kriging algorithm, there were the plates stacked, and also this little bit of a lost information, which actually prompted that cleanup process. And then finally, after the cleanup, by setting the CSF to be 1.8 and an empty interpolation, we have the ideal DTM. Now, if I compare it with the default DTM from WebODM, we can see that there's quite a bit of difference. This looks like a very usable and actual surface of land, and this is what we're going to go with. Once we've arrived at our usable DTM, which is cleaned up, I've also gone ahead and cleaned up the project space. This means grouping the layers inside of QGIS and also deleting all of these several files which have been created in the process of iterating on the different point cloud processes and also the DTM imports. So it also goes to show that there is a little bit of iteration and an art and a science to actually cleaning up the digital terrain model from a point cloud from photogrammetry, and then you can arrive at something like this. I have also gone ahead and tested out what is the difference in the elevations of the cleaned up point cloud versus the default digital terrain model, which is much more raw and aligned with the actual data capture. I noticed that the bottom portions of the valley seem very alike, plus or minus 1 meter, and at the tops it projects much higher elevation values, and by much I mean about 10 to 15 meters at the max in a 900 meter elevation, and the cleaned up point cloud is 15 meters less. So if the default original DTM was 915, the cleaned up DTM was showing about 900 in the elevated spaces, which is a safer bet to go with because it assumes and it implies that we have actually got the ground rather than the tops of the canopy.